So this is section 3.10 on implicit differentiation. And there's not a whole lot of new content here. There's kind of one main new idea or concept, and then we're just going to take what we've been doing and just apply that to the slightly altered idea. So the first big thing to think about is to think about what this word implicit means in the first place, and comparing that to actually what the word explicit, which is actually the kind of functions we normally deal with. So explicit functions are all these functions we've always dealt with, or have dealt with mainly thus far in calculus. Y equals 2x plus 3. We might see f of x equals 2x plus 3. Right? Y equals, sine of x plus 3x squared. The main idea here, right, is that the y, or the f of x, is solved for explicitly, right? We explicitly know what the equation is. The sort of opposite of that are what are known as implicit functions. And that would be something where you take this first function, you could write it as y minus 2x equals 3, and now it's an implicit function because we haven't explicitly solved for y. Similarly, you could have something like x squared plus y squared equals 9, and that's an equation where the y is not explicitly solved for, but it's still an equation. Or you can have something that's even more complicated, like sine of y plus y cubed equals 39. And in that case, maybe we can even put an x there if you want. And in that case, clearly, we cannot solve for y in this, no matter what we try to do this equation. We're not going to get y by itself, and that's clearly an implicit function. On either of these first two, we could, in theory, solve for y. We could get y by itself by moving this over and here. We could get x over here, right? Take some square roots, get pluses or minuses. So you could get y by itself in both of these first two equations, but here there's no way you're ever going to be able to do that. So any equation where the y is not explicitly solved for, we're going to call that an implicit equation. And then let's say we wanted to actually take the derivative of that equation. How do we do that? And that's what this section is about. So we're going to start with this little baby example to kind of think about how to do this. So we have y equals 2x plus 3, and we're going to compare that to y minus 2x equals 3. So we actually already know how to take the derivative of everything that we see here in front of us, and the main idea is that we're going to take an equation like this and take the derivative of both sides. So that's kind of the big idea today, is that we're going to look at an equation and take the derivative of both sides. Whatever you do to one side, you do to the other. So here we would take the derivative of this. We'd get dy dx equals 2 times 1 if you want to be super specific, plus 0, so you'd get 2. Similarly over here, we took the derivative of y. We would get dy dx. The derivative of 2 is 2, or the derivative of 2x is 2, and the derivative of 3 is 0. Right? So we took the derivative of both sides. And then we solve for dy dx. We get dy dx equals 2. So we do in fact get the same thing regardless if the equation is written implicitly on this side or explicitly over here on this side. So it's just showing you that we can take derivatives even if the y's are embedded in an equation with other things. We can do that with implicit differentiation. And the big idea is that anytime we take the derivative of a y term, the big thing that you're going to need to include a dy dx. And that's kind of the big key idea today, is that anytime we see a dy dx term, we want to add in that, anytime we see a y term and we take its derivative, we want to multiply by dy dx. Kind of similar to the idea of a chain rule, and we'll look at some examples of that as we move forward. Our first example, we're going to find dy dx for the equation x squared plus xy equals 10. So that's sort of part one. So in this case, we're going to start out, we're going to take the derivative of both sides. Keep in mind, that's the big idea. We have an equation. We want to do it to one side, we do it to the other side. The derivative of x squared is going to be easy. Here, the thing to remember is that there's actually a product there, right? It's x times y. So we must use the product rule for that guy, and then this one we know how to take its derivative. That'll be easy. So as we start taking this derivative, we're going to get a 2x plus, I'm going to leave some space there for the product rule. The derivative of 10 we know is going to be 0. So for the product rule, we're going to have x times the derivative of y plus y times the derivative of x. And if we actually work all that out, we'll get x times 1 times a dy dx. That's what you're going to put anytime you see that y prime. Plus y times 1, right? The derivative of x is just 1. We did not take the derivative of a y term there. We left the y alone, so there's no dy dx. And we have our 0. The last thing you're always going to want to do in these implicit differentiation problems is to solve for dy dx. So that's this term right here. So we're going to take everything that doesn't involve that to the other side. So it looks like we're going to have a negative 2x minus a y, and that is all equal to x dy dx. And then if we want to get what dy dx by itself, we'll divide both sides by x, and we'll get our final derivative. So that's the process of taking the derivative and using implicit differentiation. The big interesting thing here was that there was a product, so we had to use the product rule. When we took the derivative of y, the derivative of y is 1, but chain rule wise, y is not an x, so we have to take right next to it dy dx. You can think of this as when you take the derivative of x, you can put dx dx, but dx dx is 1, so that's why we don't do that every time we take the derivative of an x term. But now we're taking derivative of a term y that's different than x, so you just want to make sure you multiply by a dy dx. So this question in your notes had a second part that said to find dy dx when x equals 2. So now we know that dy dx we have in the last slide was negative 2x minus y over x. And now we need to do, we know that x equals 2, so we'll be able to plug that in, but we don't know what y is. So we need to find y when x equals 2. And to do that, you want to use your original equation. So in that equation, we have x squared plus x times y equals 10. And we know if x is 2, we'd get 4 plus 2y equals 10. So if x is 2. So if we work all this out, we get 2y is 6, so we get y is 3. So now if we come back over here, we'll have dy dx. When we evaluate that at x equals 2, we'll get negative 2 times 2 minus 3 all over 2. And if we simplify that, I think we get negative 7 over 2. And that's the value of that derivative at the point, at the value when x is equal to 2. Now I want to work maybe one more question. This time maybe something out of the book before we do the last one in the notes, just to see a few different kind of examples. So this is number 10 out of the book. And this says we want to find dy dx. And we're going to do that for the equation y to the 4th minus 2y equals 4x cubed plus x. So if we're trying to find the derivative of this, the first thing we're going to do is take the derivative of, let's start with the right hand side because that's really easy. So the derivative of the right hand side is 4. We take down the 3, x squared. The derivative of x is 1. So those are all x terms, so that's a pretty straightforward derivative. On the left-hand side, we'll take the derivatives just like we would for anything else. So the derivative of y to the 4th is 4y cubed. But because that's not an x term, we're going to include a dy dx. And similarly, too, the derivative of y is 1, and you get a dy dx. And now remember your goal is to solve for dy dx. And over here you have a dy dx in both terms. So I'm going to take that out of both terms. So I'm left with a 4y cubed minus 2. And that's all equal to 12x squared plus 1. I multiply my 4 there. And if I'm finally trying to get dy dx by itself, just remember that's 12x squared plus 1 all divided by 4y cubed minus 2. And that's my dy dx that I'm looking for in this equation, in this question. So it's literally just the process of taking derivatives. The only new thing is the idea of kind of applying the chain rule anytime you see a y inside of something else to make sure you just multiply by that derivative dy dx because you have taken the derivative of a y term, which is different than taking the derivative of an x term when we're taking the derivative with respect to x. And one more example for you, then I'm going to let you all try some on your own. So our last example that actually is back in the notes, it says to find the equation of the tangent line to x squared minus sine of xy plus y cubed equals 1 at the point 1, 0. So this one is nice because it's actually going back to our idea of finding an equation of a tangent line, but we're going to use implicit differentiation because remember the very first thing we need to do in an equation of the tangent line, what do we need? We need the slope, and the slope is, if you remember, we need to find dy dx. So here we go, we're going to find the derivative of this messy equation. We're going to go slow and check both sides of the derivative as we go forward. So we're going to start by taking the derivative of x squared. That's easy. We all know that's 2x. This next part I'm going to leave a big gap for. It's minus whatever it's going to be. And then we'll take the derivative of y cubed. Remember, that's a y term, but we still take its derivative like normal, but we just need to multiply by that dy dx term. And remember, the derivative of 1 is 0. So remember, we're taking the derivative all the way across. So don't forget to take that derivative of that 1 if you're taking the derivative of everything on the left-hand side. Now we need to go back to this sine of xy business. So remember, this is a sine, and there's this thing here on the inside. So hopefully this looks to you like a chain rule question. We have an outer function of sine and an inner function of x times y. So when we take the derivative of this, we'll take the derivative of the outer term, which is cosine. Remember to leave your inside alone, and then we're going to multiply by the derivative of that inside function. But be careful to remember that x times y requires the product rule, right, because there is product there. So we're going to come back through here, cosine of xy, and now we're going to take the derivative of x times y. So we're going to do x times y prime plus y times x prime, and then plus our 3y squared dy dx, and that all equals 0. One more line here, cosine of xy, and that's all times x times 1 times dy dx, plus y times 1, and then plus 3y squared dy dx, and all of that is equal to 0. So we've taken the derivative all the way across. The dy dx's in this case, it looks like appear a total of maybe 2 times. So we're going to leave those on the left-hand side of the equation, and we're going to move everything else to the right. So, but I guess first we need to be careful here. This cosine of xy is times 2 terms. So I'm actually going to go ahead and distribute that before I solve for dy dx. So it looks like it's cosine of xy times x times dy dx, and then another cosine of xy times y, right? Distributing this cosine of xy, it is times this entire piece of the product rule. So you get it in the first term and in that second term, and then you still have your 3y squared dy dx with equaling 0. So on the next slide, we're going to continue this work and try to get dy dx, the two, I think there are now clearly, hopefully, 2 dy dx terms, this one and this one. So we're going to leave those 2 terms on the left-hand side, and we're going to move everything else to the right-hand side because our goal is to solve for dy dx. So we don't want a combination of things because we won't be able to take the dy dx out to solve for it. So on the next page, we're going to start by leaving those 2 terms on the left. So we had a negative cosine of xyx dy dx, and then I think it was plus 3y squared cosine cosine of xy. No, not true. Let's see. I think it was just 3y squared dy dx. And then I moved to the other side. There was a negative cosine of xy, y. So I'm going to put that over here, cosine of xy, y. And there was a 2x that becomes a negative 2x as we move it to the other side. So all I did from the previous page was move stuff around so that I left the 2 dy dx terms on the one side and everything that didn't have a dy dx in it on the right-hand side. Now I'm going to take that dy dx out because it's common to both terms. I'm left with a negative cosine of xy times x plus a 3y squared. And all of that is equal to cosine of xy times y minus a 2x. And then we want to get dy dx by itself. So we have cosine of xy times y minus 2x, and all of that is divided by negative cosine of xy times x plus a 3y squared. So we found our derivative. After all of that work, we got dy dx by itself. Be very careful here. There's no cancellation that can happen, right? This term here and this term here cannot be canceled because this is one big term. This plus puts these terms together. So unless this whole entire term appears on top, you cannot cancel these cosine of xy's. So do not try to simplify this because this is as great as it's going to be. Remember, for slope, though, so we have the derivative, but the slope is a number. So we need m, and that is when you take dy dx, and we're going to evaluate it at the point 1, 0. Right? That's x equals 1, y equals 0. So remember, slope has to be a number. So you should not use this it's not your slope. It's the slope at any point, but remember we need the slope at a specific point. So that's where we're going to plug in 1, 0. So this is cosine of 1 times 0 minus 2 times 1, and all of that is divided by negative cosine of 1 times 0 times 1 plus 3 times 0 squared. So everywhere I saw an x, I put a 1. Anywhere I saw a y, I put a 0. Cosine of 1 times 0 is 1 times 0 minus 2. Cosine of 0 is 1. Don't forget the negative out front, and that's plus a 0. So it looks like I get negative 2 for my slope. Or no, positive 2, right? Let's see, because there's a negative here and a negative, so it should be positive 2. So that's my slope for this equation of the tangent line. We are now very, very close. So we have m equals 2, and we have the point 1, 0. It was very nice in this question. It gave us the x and y coordinates. So all we need to do is 1 minus 0 equals 2 times x minus 1. And we can figure that out as y equals 2x minus 2. And that's your equation of the tangent line at 1, 0 for your original equation that was given, x squared minus sine of xy plus y squared equals 1. I'm going to leave you all some questions to think about, and then you can try those, but that hopefully gives you a good sense of how to do implicit differentiation.